Hello and welcome to today's physics lecture wherein we shall be discussing about the alternating currents. But going into the deeper concepts of AC or what we know as alternating current, we would like to understand that the basic terms which are associated with this alternating current. Right? Now, as from the Faraday's law and the Lenz's law, we know that due to the change of magnetic flux within a given conductor, a current could get induced, right? And the current be such induced that it will oppose the change that is producing it. The same applies for the induced EMF or the induced charge, right? So over here, what we can say is that, first of all, let us take a circuit diagram. Say this is the circuit diagram, right? And over here there is a resistance, and this one is, say, the bulb connected to it. Okay. So this is a circuit diagram where this thing is the battery, right? And to this entire circuit, this is the power supply source. This is a key. For example, this is the resistor of, say, resistance equals to R ohm. This is the bulb, right? This kind of circuit where the major power supply source is the battery, we call this kind of circuits as DC circuits. Right? So the circuit which is known as direct current circuit, right? The direct current means that it will never reverse its phase. Yes, we are coming into the concept of phases, that what it is, what is phase change. But if we want to make it an alternating current circuit, how the circuit will look like? The circuit shall look like you could apply a key as well over here. And so this is the resistance, right? And this coil and this thing. And obviously you could add a bulb to it. So this is another circuit, but we cannot see this battery. Instead we can see this kind of symbol. This kind of symbol indicates that over here the power source, the power supply, this was from battery for the DC circuits. The power supply source is the alternating current or AC. So this is the alternating current AC, and this kind of circuits will be known as alternating current circuit or simply AC circuit. Right? Now, we have seen this battery, the presence of this battery over here as well as this like we have seen this, the presence of this bulb and this bulb, right? And also we have seen the presence of a resistance of R ohm over here as well as over here, right? But these two new things are in the concepts of AC circuits, but they are not in the DC circuits, what are they? We call them as this one as L and this one as C. Mind that this is not a battery, because a battery positive sign, it will look like a longer one and the smaller stick will be the negative side of the battery. But this has got two sticks equal, right? Now, what are this L and what are this C? As we know that R is the resistor, likewise, over here, we can write R equal to resistor. So, L over here, this L, right? We could understand it as inductor. And C, this one is known as capacitor. Right? Now, in the AC circuits, we can observe all of them. Right? For example, it will be a purely resistive circuit or purely like inductive circuit, purely capacitive circuit, or RC circuit, or RL circuit, or LC circuit, or LCR or RLC circuit, right? It could be the combination of all, or only single and individual, right? So these things are the components which could work under these AC circuits, and obviously into the entire series description of alternating currents, we are going to take a look at those. Now, about the AC or the alternating current, this goes about the circuits, right? Now, first of all, as we have mentioned that with the induction of this Faraday's law and the Lenz's law, with the introduction of them, we could know that the change of the magnetic flux could produce a current, and the current will be as such. The previous, what I have told, is about the Faraday's law, and now the Lenz's law states that the current that is produced now within the circuit will be as such, the direction will be as such that it will oppose the change that is producing it. Right? So in this scenario, a current will be produced. Now, for example, a current is being produced in two rods like this, right? And the change is happening and we are getting the current on the clockwise direction, right? Now, if we reverse them, if we do that, this is a kind of a frame, and if we do reverse them, over here we have seen that it is going up in the green pin or in the green side. And over here on the blue side, we are saying that it is going down. Then only it will be clockwise. But if we manage to reverse this frame, right, we will know, so this is coming down and this is going up again, right? So now in an anti-clockwise direction, current will flow. Let us say it how. For example, observe carefully. This is a frame. Right? And we are like the magnetic flux is changing with respect to time. Right? So we can say that ddt component of this phi magnetic flux is not equals to 0, which means that this is not a constant term, right? It is changing with respect to time. So if it is changing with respect to time, and if we take that on the red side, it is going up. This side, this will go over on this side, and now it will come on the downward side in the blue, and now like this. So this will be a clockwise current, right? Obviously this current will be produced as such that it will oppose this direction of flow of this current which is induced, right, will be directed as such that it will oppose the change that is producing it, right? Now for example, if we manage to rotate this frame, so the blue will come over here and the red will go over here, we are going to rotate this frame now, okay? So now we can see like this, it will be rotated. In the red mark side, we have seen it will go up. The current will go up, right? So it will go up over here also, right? If it goes like this, obviously it will go likewise. And in the blue mark, right, we have seen it is going down. Now see, it will also go down, right? So it will make another direction like this. Now look and observe very minutely. This is clockwise, right? But on the other hand, this is anti-clockwise. So now we are going to, first of all, we need to change this magnetic flux, and if we are going to rotate this frame upside down, we are going to see that first of all, a clockwise current is being produced and then an anti-clockwise current is produced, right? So we will see that if we are going to make a graph, that this will be, for example, I, and this is, say, for example, the time we take it for. So we will see that first of all it will go up on the positive side of the clockwise direction. It will attain a maximum value, will come down to 0, will again attain the maximum value on the negative side, and then again go back to 0, right? So the curve will be something like that. But experimentally, it has been observed that the alternating current curve actually follows a sine wave form. So this kind of curve is only meant for your understanding, preliminary understanding, but this is not the waveform of an AC circuit or of an alternating current. So how will be the wave of an alternating current look like? As it has been experimentally observed that there is alternating current or the alternating EMF, right? This will follow a sine wave curve or a sine wave form. So it will attain a maximum value, come down to 0, and attain a minimum value and again come down to 0. So this is the actual curve of an alternating current. Over here we could take this axis as, this is for, say, like the induced EMF, and we could take this axis as for time. So watch carefully. First of all, it has started from 0, right? This is the 0 point, the origin. It has started from 0. It will rise up, say for this is the clockwise, okay? It will rise up and attain a maximum value. this maximum value of the EMF or the induced current is known as the peak value, right? And after that it will again come down to 0. Now it will reverse the direction. It will come back to this point, attain the maximum value on the reverse direction, and then again will go back to 0, right? This is the completion of one phase, because we know that sine curve, it changes like this value from 0 to 2 pi. If we take 2 pi plus theta, sine of 2 pi plus theta, the value will be equals to sine theta, right? So this is known as one phase of this alternating current. Okay. Now minutely observe that this one up till this is known as the half cycle. Likewise, this area for this is known as another half cycle. Right? If we take, for example, that the alternating current, this kind of waveform, it takes the time period is capital T, which means to cover from over here to over here, it will take the time of capital T. Right? So, if we take that this time, this is equals to capital T, right? So, this half cycle time, what it will be? The time of the half cycle then will be T divided by 2. This will also be equals to T divided by 2. So, now we can say that this alternating current, as a definition we could say that alternating current is that current which changes its magnitude, because this will be either E or we could state it as I with respect to T. So the alternating current will be that current which changes its magnitude with respect to time and periodically changes its phase. This is a period. After every pi, it will change its period. This is pi by 2 and this is pi. After every pi, it will change its phase. The half cycle is up to this, then again half cycle on the lower side, then again half cycle on the upper side, then again half cycle on the lower side, likewise. So, the alternating current is that current which changes its magnitude with respect to time and periodically it changes its phase, right? And the same also applies for the alternating EMF. This alternating EMF, right? Now the equation of this alternating EMF, what it has been found out is at any particular time when we are looking at this curve, right, this EMF will be equals to E naught multiplied by sine omega t. Now this E is the actual position or time we are looking at. So this E basically it depends on this time or t. For example, at 2 second time, it is starting from t equal to 0 second. At 2 second, after 2 seconds, this is over here, right? And if we want to know the EMF of this, right? Obviously the EMF is changing, right? For every moment. So we want to know the EMF at time when t equals to 2 seconds. At that moment, it will be calculated as E naught, which is known as the maximum or the peak value. The maximum or the peak value will be this one. Again, this will be equal to this one. E naught. This is again equals to E naught, right? So if we take a curve, right, the alternating current like this, so for example, this will be both the same, okay? So the maximum EMF that it attains on any side, on the upper side or the lower side, it will be the same, the E naught. So this point will be E naught when we are taking this curve with respect to the EMF and the time, right? So this is that E naught or the peak value of this EMF that could be attained, right? Multiplied by sine of omega t, we could understand that this t is equals to time, right? But what is omega? To understand omega, first of all, we have to understand this is a waveform, right? And it has got a time period, as we have said that t is the time period over here, t. Right? Now, as for frequency, what do we know? That frequency is the measure of the number of complete cycles that will be covered in 1 second time, right? So if we take frequency as small f, we can write that it is equals to 1 by capital T, where f is the frequency and t is the time period, right? This term indicates frequency and this term t indicates the time period, right? Now the omega, as we know that this is the frequency, right? We have to now understand the angular frequency. The angular frequency is being represented by omega, and the value of this angular frequency, omega, will be equals to 2 pi f, or 2 pi multiplied by the frequency, right? And or it could be written that omega is equals to 2 pi divided by t, because we know that the value of f equals to 1 by t, so we can replace the value of f as 1 by t, and we can write omega is equals to either 2 pi f, or we can write the value of omega as equals to 2 pi divided by t, or the time period, right? So now we have understood over here that what is omega, what is the t, what is E naught, the peak value, and what is the E. Now, why have we taken this omega t? Because this will be likewise E naught sine of omega t. So omega t is now been seen as an angle, right? Now if omega t is being seen right now as an angle, what is omega t? This omega t is known as the phase. Now what is phase? We need to understand that. For example, in this curve, look minutely, this is 0, right? How could we understand that what is the magnitude of the E right now? Okay, because this is in angular terms, right? This is not a linear motion not going on, this is a waveform. So, to understand the phase change could be depicted as, it could be defined as that phase change is defined as the time elapsed from the moment when this alternating EMF or the alternating current it last past its zero value in the positive direction, right? So we could write phase change as it could be defined as the phase change could be defined as the time elapsed. Time elapsed from which point? Since the alternating EMF or current last past its zero value in the positive direction, right? So we can define the phase change as the time elapsed since this alternating current is now over here at any point, but from which point we are going to see? Since the alternating EMF or the alternating current last past is zero value is over here, zero value is over here, and zero value is over here. 3 points, right? Last pass is zero value in the positive direction. See, this one is going down. It is passing the zero value in the negative direction. So this won't be. This is going in the positive direction, surpassing its zero value. This is also the case. It is going in the positive direction, right? So, for example, we are taking the point over here and we are going to understand that how much E it will be, right? So, we need to find out the time. But how much time has elapsed, right? What is the frequency of this alternating EMF or alternating current? Or if you are not given with the frequency, what is the time period of this waveform, of this alternating EMF, of this alternating current? So we can find out the omega. The omega now multiplied with this time, the small t, it will give us the phase change, right? So this will be basically the phase change. So this will, the omega t will give us a phase change, right? So the sign of this phase change when multiplied by the peak value of this EMF or the peak value of this alternating current, it will such as give this point's EMF or this point's alternating current, right? So in the subsequent lectures, we will be trying to understand. We have seen over here this is for the equation of this alternating EMF, right? And also we have understood the major and basic difference between the DC circuits and the AC circuits, and like how could we actually produce. And the methodology in which, the procedure by which it could be produced would be the AC generator, which we will be discussing later on. And over here we could see that d phi divided by dt, or the dt component of phi, is when it is not equal to 0, which means the flux is changing with respect to time. Taking the Faraday's law into remembrance, we could understand that an induced current or an induced EMF now will come into play, right? And according to the Lenz's law, this induced EMF or the induced current, the direction will be as such that it will oppose the change that is producing it, right? Likewise. But if we now are going to change this frame, then we will see that the clockwise current is now being reversed into this anti-clockwise. This clockwise is now reversed into the anti-clockwise. But mind that this half cycle, both will have the same time, and that will be equal to the time period divided by 2. And also, the peak value attained by either this E or this I, or this EMF or the current on the positive side will just be equal to the peak value which is obtained on the negative side or on the reverse direction, right? So over here the alternating current, it could be defined as that current which changes its magnitude, because always it is changing its magnitude, right? It changes its magnitude with respect to time, but also it changes its phase after a certain time, right? Or it periodically changes its phase. That will be better, because every after pi it will be changing its, like every after t by 2 time of half cycle it will be changing its entire phase. And after that we have seen the equation of this EMF, alternating EMF, and this phase change we have understood that what is omega. The omega over here is the alternating frequency. We could write it that over here the omega is the not alternating frequency, it will be the angular frequency, as we have seen that this is the frequency of small f. So omega will be the angular frequency. The formula would be 2 pi f, or 2 pi divided by capital T, where capital T is the time period, right? And the sine of this angle when multiplied by to the peak value of this alternating EMF or alternating current, it will give us the value of alternating EMF or the alternating current respectively. In the subsequent lectures we are going to understand the difference and the relation between the peak value, as we have seen over here. We are going to understand the major differences and what are the relation between the peak value, mean value, RMS value. Thank you. Hello and welcome to today's physics lecture in continuation to the previous lecture about alternating current. So in the previous lecture we have studied about the alternating current, and we have seen the equation for the alternating EMF at a given particular point of time. So the equation which came out was E equals to E naught multiplied by sine of omega t, right? Now for example, if we draw a circuit as such, this will be the AC supply, and over here there is a resistance of say R. This is the resistance of say R, right? And at particular instant we know that the alternating EMF as E. So the current that will be over here known as the alternating current, alternating current, right? From the famous Ohm's law, we could get the equation as I now will be equals to E divided by R, right? Now, if we replace the value of this alternating EMF with this equation, what we can get is equals to E naught divided by R multiplied by sine omega t. Right? And this E naught divided by R, the peak value of this like alternating EMF, and it is divided by this resistance of R, it will come out to be the peak value of this alternating current. Right? So, as primarily we have got the equation as E will be equals to, at that particular point of time when T is equals to that thing, small t. So, at that point of time the alternating EMF will be equals to the peak value of this alternating EMF multiplied by the sine of the phase change. Right? Likewise, the alternating current at a given particular point of time will be defined as the peak value of this alternating current, right, multiplied by the sine of the phase change, because omega t, this is, as we have known earlier, that this is the phase change, right? Now we wish to find out the mean value of this alternating EMF or the alternating current, right? The mean value. The mean value of this alternating current is defined as, see, this one is the peak value. We could write it as the peak value. Likewise, E naught will be the peak value for the alternating EMF, right? So, the mean value will be defined as I suffix m, which stands for the mean value of alternating current. So, the mean value of this alternating current may be defined as the steady current, right? As we have seen in the graphs, that the current, alternating current, it always changes its magnitude with respect to time, but this mean value of alternating current will be the steady current, right? So, the steady current that will send the same amount of charge over the half cycle, which means time is t by 2, right? As the same charge will be sent by the given alternating current in the given time of half cycle, that is t by 2. So we can write it as, may be defined as the steady current that will send same amount of charge within half cycle, which means over here the time is equals to t divided by 2, as the charge. So if the steady current that will send the same amount of charge within half cycle as the charge amount in the circuit by the given alternating current, but over the same half cycle time, over its half cycle, within bracket, where time is again equals to t by 2. Right? So, let us draw the graph. The graph will be as such. Now over here, if we wish to draw right, this is the peak value of I naught, and this is over here we measure the current. This is where we measure the time. So this part will be equals to, this will be one half cycle, then this will be another half cycle. So over here, this part is a half cycle. And if this is a half cycle, the time at this particular given point, t will be equals to 0, right? And the time when the half cycle is completing, the time will be equal to capital T divided by 2, where T is the time period for covering up this entire one. Right? So, as we know that Q or the charge is equals to I integration I with respect to dt, right? Because we know that current will be equal to the change of this amount of charge with respect to time, and we could take this integration within the limit of t equal to 0 to t equal to t by 2, right? So the lower limit will be 0 and the upper limit will be t by 2. So we can write the value of I as I naught sine omega t, and as I naught is the constant, it will come outside, is equals to I naught integration from 0 to t by 2 of sine omega t dt, right? And as we know from the laws of integration that the integration of sine theta or sine m theta d theta will be minus of cos m theta divided by m. So we can write this equation as equals to I naught multiplied by minus of cos omega t divided by omega. And what will be the limits? From 0 to t by 2? From 0 to t by 2, right? So, putting up the values over here, we will get, now, as we know that omega, the value of omega is 2 pi divided by t, as we have discussed earlier. So the value of omega now could be replaced right? As this is a constant, this could go outside. So it will look like I naught capital T divided by 2 pi, right? Why? Because the value of omega that is now over here will be replaced by 2 pi multiplied by capital T, and we could do, like this is a negative sign, so we could change up the limits. So this will be cos of omega t divided by omega from now t by 2 to 0, right? So it will come up to be as I naught t divided by 2 pi, now multiplied by cos of omega t. Let us see what will be the value of this cos omega t. Sorry, we could not take this omega because we have already taken it out, right? So what is the value of cos omega t? We are going to replace now t by these two values, right? So the cos omega t, basically we can write it as cos of omega t, we can write it as cos of 2 pi divided by t multiplied by the time, right? So first of all, we will get it as, this is cos omega t, means this one, where the first t will be replaced by 0. So the entire term will become 0, cos 0. Minus. Now this small t will be replaced by t equals to capital T by 2, right? So this will come out to be, if we put t equal to t by 2, we could see it likewise, cos of omega, this t is over here t by 2, it will be cos of 2 pi divided by t multiplied by t divided by 2. So we can easily cancel out this 2 and this 2, this t and this t. The left out is only cos pi. So this will be cos 0 degree minus cos pi, right? And now what is the value of cos 0 degree? That is plus 1. And what is the value of cos pi? This will be minus 1. So we can write it as I naught t divided by 2 pi, 1 subtracted by being minus 1. So this minus and minus, it will become plus or positive. So this will be 1 plus 1 equals to 2, right? Or we can write it as I naught capital D divided by 2 pi multiplied by 2. So over here, we could cancel out this 2 and this 2, right? So the net out expression for the Q will be equals to I naught T divided by pi, right? And as we know now that the value of this I or this IM or the mean value will be equals to this Q divided by what? The time? What is the time over here? The time over here is T by 2, right? So this is T divided by 2. Now what is the value of Q? This is the value of Q what we have observed. I naught multiplied by T divided by pi. So we can write I naught multiplied by T divided by pi. And the time, this will be T by 2T. And this will be over here. The denominator's numerator will now be the numerator, right? Over here, we could see that we can cancel out this capital T and this capital T. So the left out expression over here, we can see it as equals to 2 divided by pi multiplied by I naught. So the expression to which we have reached is that the mean value or the I mean will be equals to this term or 2 divided by pi of I naught. Right? And since we know that the value of this pi will be equals to 22 by 7, so if we find out the value of this 2 divided by pi, we are going to observe that it will come out to be Im will be equals to 0.637 multiplied by I naught, which again implies that or we could write it as I as mean is this is I mean will be equals to 63.7% of I peak, because I naught is a peak, right? So now we have reached to a conclusion or the relationship between this I mean or the mean value of this alternating current is equals to 63.7% of this peak alternating current. So if this is I naught, we could find out a point somewhat like this. This will be equals to Im now, right? And this Im will be 63.7% of this I naught. Okay? So now we are well through with this, what a mean value of this alternating current is about. In the subsequent lectures, we will be studying about the RMS value of the alternating current. Right? Thank you. Hello and welcome to today's physics lecture in continuation to the alternating current, where we have previously seen that the mean value of an alternating current. Previously we know that I is equals to I naught multiplied by sine of omega t, where I is the alternating current value for a given time of t, right? Now we shall be discussing about the RMS value, which is known as the root mean square value. And this RMS value is being denoted by either I suffixed by RMS or suffixed by V, right? Now this root mean square value of an alternating current is also known as the virtual current or the effective current, right? So for this virtual we have taken it as IV. Now what does the root mean square value of an alternating current basically says us about? It says that the root mean square value is of an alternating current obviously is that steady current that which will produce the same heating effect circuit, right, within a given particular interval of time. Within a given time, as the heat that will be produced, as the heat produced in the same resistance of the circuit in the same time. If we take this time as t, now let us see that what it actually says us about. The root mean square value or the virtual current or the effective current of an alternating current is that steady current which will produce the same heating effect in a given resistance of a circuit within a given interval of time, say capital T, as the same heat produced in the same resistance of the circuit in the same time of capital T. Now, for example, if we take up a circuit of alternating current of, say, this is the resistance of, say, capital R, and over here the current flowing is I. So obviously, if this alternating current passes through this resistance for a given certain interval of time, a heat will be produced. And we know that the formula of the heat produced, where Q is the heat produced, the formula of this heat produced will be equals to the integration. Now we are taking it from 0 to t, the time interval, of I square multiplied by the resistance multiplied by the time t, right? And this will be for a small time interval, so this will be dt, as we are integrating the time now from 0 to capital T. Now, as we know that the value of I at a certain given point of time is I naught sine omega t, so we can replace this value of I with that, right? So we will get it as integration from 0 to t of I naught square multiplied by sine square omega t, right, multiplied by R dt. Over here, this I naught is the peak value and it is a constant value, and this resistance R, will it change with respect to time? No, this is a fixed resistance, so this is also constant and it will come out. So we can write it as I naught square multiplied by R, the integration from 0 to t of sine square omega t dt. Now, from the trigonometry, we know that sine square of, if we take this as m theta, it will be equal to 1 minus cos of 2 m theta divided by 2. Right? We could find it out from trigonometry. So now we are going to replace the sine square omega t by 1 minus cos 2 omega t divided by 2. Okay? So this will come out to be as equal to I naught square r integration from 0 to t, and we can write it as 1 by 2 minus cos of 2m theta divided by 2. So if we write this 1 by 2 dt minus again integration from 0 to t of cos 2m theta, cos 2 omega t, cos 2 omega t dt, and this divided by 2, and this will be inside this whole bracket. This will be multiplied by I naught square r. Right? Now if we perform the integration, it will come out to be as I naught square r multiplied by, this is 1 divided by 2, this integration of t, it will be t from 0 to capital T, right? And this will come out to be minus 1 by 2. This 2 is a constant. It will come outside on the denominator side. Okay? And the integration of cos 2 omega t, right? It will be of sine 2 omega t divided by 2 omega, right? Within the limits of from 0 to capital T, and this entire thing will be inside the bracket when multiplied by I square multiplied by R. So we can find out this is equals to I naught square multiplied by R. So this will be T, capital T minus 0. So it will be equals to T divided by 2 simply, right? Minus, it will go as 1 by 2 multiplied by 2 omega, because 2 omega is a constant over here now, and now we are replacing this thing capital T and 0 in place of T. Now for T equals to 0, if we are going to find out for T equals to 0, we will find that it is completely 0, so sine 0. And if we are going to put this capital T over here, then what we will get? This 2 omega t. We have to find out first of all this value of what is 2 omega t. The value of 2 omega when t is replaced by capital T, it will be equals to 2 multiplied by 2 pi divided by t, because we know that the value of omega is equals to 2 pi f, or 2 pi divided by the time period capital T multiplied by this capital T. We have taken this capital T as the time period, right? So we can understand that this t cancel out this t, and the value will be equals to 4 pi, right? And if this value is equals to 4 pi now, so we can write this sine of 4 pi minus sine of 0, right? Now what is the value of sine 4 pi? It is equals to sine 0. And what is the value of sine 0? It is equals to 0. So this will be 0 minus 0 will be 0, and this 0 when multiplied by this term, again it will go 0. So the only left out term is this one, and this will be multiplied to this. So we could find out is equals to I naught square divided by 2 multiplied by R multiplied by T. Now watch out. This is the actual term, and for this particular given, the steady current, the value will be IV. So what amount of heat it will generate? It will generate the heat as now Q equals to IV square multiplied by RT, right? So if we give it as equation 1 and this as equation 2, it says that the same amount of heat will be produced. This means that this will be equal to this. Now if we are going to equate 1 with 2, we will be finding out that I naught square divided by 2 multiplied by RT will be equals to IV square multiplied by RT. Over here, this R will be cancelled out, this R and T will be cancelled out with this T. So now the expression will look like this will be IV, or the root mean square value, that will be equals to I naught, or the peak value of this alternating current, divided by under root 2. And if we make it out, the value of 1 by root 2, we are going to find it out 0.707. So we can write over here, this value will come out to be IV will be equals to 0.707 I naught. Right? This is the value of this root mean square. Okay? So we can write this RMS value, or we can write simply as IV will be equals to 70.7% of peak value of I, or we may say it as the peak value is I naught, right? Now if we could look at the curve, we could find out that for an alternating current which we have seen the sine wave form, and if we make it likewise, we will see that there is a sine wave form, for example, somewhat like this, right? This is 0, this will be 2 pi, and over here we will be taking I. The graph will be with respect to the time elapsed, right? So the steady current, the value of this steady current, which will produce the same heating effect as for the same time taken as it would be for this alternating current, right? For the same time, this will be I naught, this value, right? So the IV will be somewhere over here. This green, this is the IV, or the root mean square value, right? So the root mean square value will be like this. At this point, this will be the steady current, what we have looked out for this. And as we know that this is the peak value, This IV is basically 7.707 I naught. That means it is 70.7% of the peak value, that is I naught. Right? So in the subsequent lecture we will try to understand the relationship, as we have found out that this is for I. Right? In the subsequent lectures we will try to find out that what would be the relationship for E, or the alternating EMF, right? And what could be the graphical representation of them, and how we could find out that what actually is meant by the effective voltage of an AC. Thank you. Hello and welcome to today's physics lecture, wherein we shall be discussing about the alternating currents. In the previous lectures we have discussed that what would be the alternating current look like, what would be the mean value of an alternating current, right? And like what would be the effective or the virtual value or the root mean square value of an alternating current. Now in this lecture we shall try to understand the values for the alternating EMF as well, right? So first of all, as we know that this I is equals to I naught sine omega t. This was the basic equation, right? So we could write that E will be equals to E naught sine omega t, right? Because this is the same as we have defined that this alternating current, that it changes its magnitude with respect to time and periodically reverses its phase. Likewise, this alternating EMF, the definition will be the alternating EMF changes its magnitude with respect to time and periodically changes its phase, right? So for example, if we take out, this is the curve for the current, and say for example we check out another curve for say now the alternating EMF. So over here now we will be taking both with respect to time, because it changes its magnitude both I and E with respect to time. So this will be with respect to time, as well as this curve will be with respect to time. But over here we will be taking the values of I, or the alternating currents, and over here we will be taking the values of alternating EMF, right? And now, as for these two given equations, we can draw a graph. The graph will look like this for alternating current, right? And as well as for this alternating EMF, the graph shall look like now. Both are actually, they are obeying the sine wave form, as we could see in this equation, right? Over here the omega t is the phase change, right? And the highest value of this I, or the peak value, as we know, will be I naught. So this particular value will be I naught, right? And this particular value will again be I naught, but on the reverse side, so we will take it as minus I naught, right? And this will occur for which time? At what time? For the time drawn on this time axis. And likewise, we could go over here. As of for the alternating EMF, we could see the same equation likewise, where it is denoted by the peak value of this alternating EMF as E naught. So over here we could take this is E naught and this will be minus of E naught, right? And for which time? Draw the perpendicular, this is the perpendicular line obviously, on the time axis, and we are going to find out that actually what time did it make its peak value. So this is I naught or E naught or minus E naught or minus I naught are the peak values of this for the alternating current and this for the alternating EMF, right? Now as we know that for the mean value Im is equals to 0.637 I naught, right? Likewise, the EMF, if it is calculated for the half cycle, the mean value for this EMF will be found out to be 0.637 E naught, right? So now, if we want to locate out this mean value of I, go into the IT curve, the mean value 0.637, say for example it will be somewhere like this, right? This will be the corresponding time. Likewise, over here, and so this is the corresponding time. Okay? We are showing it in only one side on the positive of I and one side on the negative side of I. So this will be the value of Im and this will be the value of minus Im, right? Likewise, the same goes for this EMF. This is the mean value of this alternating EMF, and likewise this is again the mean value of alternating EMF, but this will be provided with a negative sign, right? Now for the another equation, we know that for the RMS value or like the effective value or the virtual value, we found out that IV will be equals to 0.707 I naught. Likewise, the virtual value of this alternating EMF will be equals to 0.707 E naught. So, if we want to locate out this point, we could find out like this. So this value will be IV, this will be minus of IV, the same applies here, this will be EV, and will be minus of EV, right? So from this entire graph we are able to understand that the mean value of the alternating current or the alternating EMF is actually the least, whereas the peak value for this alternating current or this alternating EMF, take it for any direction, either in the upward direction or the lower direction, as it changes its phase periodically, the peak value is I naught or E naught, right? And over here we could see that 70.7% of the peak value for this current, alternating current, as well as this alternating EMF, there comes a value of IV, which we actually know as the virtual. Now it is also called as the effective alternating current or the effective alternating EMF. Why is it called effective? Right? It is called effective because if we connect a voltmeter across an AC circuit, we will get the reading from that voltmeter as equals to EV. We are not going to get the reading of E naught, and that is the reason why the AC or the alternating current, it is regarded as much more dangerous than the direct current, right? Now, as for this, for example, we are taking another curve now for showing the mean value and the RMS value. Actually, what does it represent? So, for example, we are taking for I only, for the alternating current, and this is the curve, right? So we have taken over here this as I, and over here we have taken as T, right? So we can understand that over here, if we take a very small interval, say for example we are dividing, this is for the entire time period of T, right? And now we are dividing this entire time period into, say for example, 1, 2, 3, 4, like 8 parts, okay? First, second, third, fourth, likewise, fifth, sixth, seventh, eighth. We have subdivided this entire of time T in 8 parts. And each part, for each part, this part or this part or this part, it will be having an instantaneous value of alternating current, right? When it will be possible? If we are going to take this interval as infinitesimally small, right? So, for example, if we are getting this one as I1, this one as I2, this one as I3, this one as I4, likewise I5, then I6, I7 and I8, right? And we have divided this time into 8 parts as well. So the mean value of the current that will come out to be for IM. We are now going to represent that what actually the mean value of, and this is the mean value, this, what does the mean value of an alternating current or the mean value of an alternating EMF actually represent, right? So watch and observe carefully. This mean value will just be equal to the summation of all these currents what we have taken. So this will be I1 plus I2 plus I3 plus I4, likewise up to I8, and this will be divided by 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 intervals, right? So this will be divided by 8, right? And what does actually this EV or IV, this effective value or the virtual value, actually represent? Let us see. If we take for this case now, we are going to find out the IV. This is represented as whole root over of I1 square plus I2 square plus like this I3, I4 up till I8 square, and this will be divided simply by 8, right? So we could write Im as equals to the summation of I, where I is equals to 1, and this will be summated for up till n, divided by the number of observations n, right? So this is basically what we mean by this mean value. The same applies for EM, right? If it is EM, then it will come as EI. The rest will remain the same. And for this particular IV, what we can write as? We can write it as IV will be equals to under root of summation of I square, for I is equals to 1 and it will be summated up till n, whole divided by the number of observations or the number of parts in which we have broken up in, right? So divided by n. So this is actually what is represented by the effective value or the virtual value, or this like IV or the RMS or the root mean square value is denoted by IVEV, right? And the same applies for the phase change on the opposite side, on the negative side, right? So this is all about what does the alternating current, alternating EMF, alternating circuit, like we have seen that in the DC circuits we could find out only the resistance, but in an AC circuit we can find out the resistor, the inductor and the capacitor, right? These three things, and how we can form a circuit making a combination of them in different formats. So we have understood the equation of this I and E. After that, we have understood the relationship between the peak value and the mean value, and the relationship of the RMS value with the peak value, right? And afterwards we have understood that what actually the mean value or the RMS value or the effective value is all about. So in the subsequent lectures now, we will be diving deep into the alternating currents to understand that how the resistor the like capacitor, the inductor, it could be made in a circuit and the AC is passed through it. The main and the interesting part, it will be the phasor diagram. So for the phasor diagram, just look out for more videos. Thank you. Hello and welcome to today's physics lecture, wherein we shall be discussing about the advantages and disadvantages with the alternating current versus the direct current. So let us check that what are the preliminary advantages of an alternating current over DC. So first of all, the advantages, we shall be listing them out, right? Now, as we know that this alternating current with the formula of the angular frequency as omega, where omega equals to 2 pi f, we know that this alternating current is available in a wide range of voltages, right? So, number one, AC is available in wide range of voltage. Right? This is not the scenario with the direct current. The direct current is not available in a wide range of voltages. Right? The second important point is that economically, this usage of this alternating current is very effective, which means that it incurs less cost. Number two, it incurs lesser cost, right? Now, as this is getting a lesser cost, this should be the case that in maintaining the entire operation with this alternating current, it must be having a very less overhead. So, the maintenance of this kind of things is very less. So, we can write as, in point number 3, it incurs very less maintenance, right? Since it is incurring lesser cost, then obviously it is incurring a very less maintenance, right? Now this AC is basically very simple and robust. It is simple and robust, and we could say that it incurs very less maintenance, so it incurs less care, right? The next point is that the supplying AC at high voltages, by supplying this alternating current at a very high voltages, we can minimize the line losses. Supplying AC at high voltages it minimize the line losses, right? And this alternating current, it could be controlled without much wastage of power with the usage of a choke coil. Right now, what is a choke coil? We shall be understanding it later on. So, this could be this alternating current, it could be controlled this AC could be controlled without the alternating current, it could be controlled without much wastage of power. Much wastage of power with the help of a choke coil. Right? Now, this alternating current, it could be easily converted. Right? This alternating current, it could be easily and conveniently converted into direct current, right, with the application of rectifiers. Well, with rectifiers, right. Now we shall be discussing about the disadvantages. This we have seen the advantages of the AC over DC. Now we shall be discussing about the disadvantages of an AC or an alternating current with the DC or over DC. So these are the disadvantages. Right? The first and foremost disadvantages of an AC is that it is highly dangerous. Number one, it is highly dangerous as compared to the direct current. Right? Now, as we have seen earlier while discussing between the mean value, the effective value and the peak value of an alternating current, over there we have seen that the effective current that is being measured, this was actually 70.7% of the peak value. So, in a circuit where the power supply is of an alternating current, the voltmeter will read only 70.7% of the peak value of alternating EMF. Right? And thus, it is dangerous also. So, the effective value of voltage is measured by voltmeter, the instrument which is used to measure the potential difference across or the potential drop across 2 points. So this will be basically 70.7% of the peak value Right? Now, this alternating current has got a behavior known as skin effect. Now let us understand what a skin effect is. It shows behavior of skin effect. Now, what a skin effect basically is. For example, this is a conductor, this is a wire, and the alternating current is been passing from over here, from this point to over this point. But the alternating current is not going basically inside this wire. It has a tendency to remain on the surface of this conductor. And this thing is known as the skin effect, right? The next point is that several applications like, say, applications, or to be precise, we can say it as industrial applications, right? Industry oriented, like, say for example, electroplating, electrotyping, say for example, electroplating, electrotyping, okay. So this, like this industrial application like electroplating, then like electrotyping, and this electro-refining and electro-refining could only be done by a direct current. It could not be done by an alternating current, right? Could only be done by direct current or DC, right? And last but not the least factor is that this alternating current, though it is available in a wide range of voltage, but still it is not available in pure frequencies. So, last point, it is not available in pure frequencies, right? So now we are well through with the advantages of an alternating current over the direct current, and what are its disadvantages of this alternating current over the direct current, right? Thank you.